Okay, we're going to be going over the evidence for plate tectonics here. Now, the first bit of evidence is the matching coastlines of South America and Africa. The idea that the continents moved is as old as most accurate maps. As soon as these became available, people began to notice how similar the coast of Africa and South America are to each other. This gave rise to the theory of continental drift. In addition to similarities of South America and Africa, there are several other pieces of evidence to suggest that plate tectonics is occurring. So evidence number one, matching coastlines. The coasts of Africa and South America appear to match up. Evidence number two is that heat, age, and magnetic orientation of the rocks at the mid-ocean ridges. Now, heat flow. Heat flow measures the amount of heat leaving the rocks in the lithosphere. The heat flow measurements have repeatedly been the highest at rocks found in the mid-ocean ridges. This means the rocks at these spreading centers are recently formed from magma rising to the Earth's surface. So, in other words, at the mid-ocean ridges, we see that those rocks are the hottest, most likely because they were recently magma. Now, age. Using radiometric dating, we can determine the age of rocks in the Earth's crust. We will discuss exactly how this is done in the next unit. Radiometric dating has shown us that the rocks found at the mid-ocean ridges are the youngest. In addition, we know that as you move further from the mid-ocean ridges, the rocks become older and older. This pattern of aging is symmetric on both sides of the ridge. This tells us that new rocks are constantly forming as the spreading center then pushes outwards as the diverging boundary moves. So evidence number two, age, heat, and magnetic orientation. The first part of that was the rocks at the mid-ocean ridges always have the highest heat flow because they've recently cooled. The second part, the rocks near the ridge is always the youngest, and it gets older as you move away from the ridge. Okay, the last bit is kind of interesting. Most people don't realize that the magnetic orientation of the Earth actually switches about every 14,000 years, and that's recorded in these rocks. As these rocks cool, they record very, very slightly which way the orientation of the magnetic field is in the Earth. So magnetic materials within the igneous rocks that form from cooling magma are oriented pointing straight at the magnetic north. However, every 14,000 years, the magnetic poles of the Earth reverse, meaning magnetic north moves under Antarctica and magnetic south is under the Arctic. Because of this reversal, the bands of the igneous rocks created at the spreading centers create distinct bands of rocks that can be differentiated by the way the minerals are aligned. For 14,000 years, all of the rocks formed at the center spreading will be pointing north. The next band, the minerals will be pointing towards the south because that's where magnetic north is. It switches back and forth and back and forth. Like the age, the magnetic pattern is symmetrical on both sides of the ridge. That means on this side of the ridge, it'll be facing north, just like this side. But then if we move one step out this way, it's facing south and facing south on this side. So as we travel further and further from the spreading center, the rocks get older and older, and the magnetic orientations of the rocks changes with the magnetic pole reversals. Here's how you could summarize all of that in one little paragraph. The magnetic orientation of the rocks switches as you move away from the ridge. My hope is that as we read, and if you can read and understand this, you can see how you can turn that into Cornell notes. Now I would add a drawing here where you have a mid-ocean ridge with some bands coming on either side, and you need to mark, this will be north facing, here's south and south, north facing, south. You can also add age because the age graph will look exactly the same. Evidence number 3. Volcanoes and earthquakes. Earthquakes don't occur randomly across the world, but happen across limited belts which also contain most of the world's volcanoes. These belts mark the location of the plate boundaries. These areas are so active because of the stress the two plates sliding against each other and eventually gives in the form of a volcano or an earthquake. The largest belt of activity is the Ring of Fire surrounding the Pacific Ocean, which is home to 90% of all quakes. The Ring of Fire surrounding the Pacific Ocean includes 90% of all earthquakes and most volcanoes. Here is a graph that shows the locations of all the earthquakes happening in the world. And what you'll notice, as the days tick by, it's keeping track of about the last 200 of these earthquakes, and they're all happening in about the same area. They're happening here, through here in Malaysia, off of Japan, in this part of Alaska especially. There's a ton going on here. The west coast of the United States, Mexico, South America. This is what we call the Ring of Fire. However you want to get that into your notes, I think it's important that you try to at least sketch it, give you something to remember. All right, the last bit of evidence is fossils on different continents match with each other. Now, paleontologists have found that bones of the exact same species of organisms on continents that are separated by vast oceans. It is extremely unlikely that the same species evolved twice in two different places. It is equally unlikely that land-based animals could migrate across an entire ocean to survive. The only rational explanation left is that the two continents were once together and the organisms were roaming together over them. Last bit of notes. Fossils of the same land-based organisms has been found separated by vast oceans. Here's a closer look at that map. South America, we see a fossil remains of a Triassic land reptile, 3 meters long. Those fossils are found in very similar rock layers, so it seems like this was once together. Similarly, fossil evidence of a Triassic land reptile, Lithosaurus, it was found in this part of Africa, Madagascar, India, and down into Antarctica. The only way that it seems that this could happen is if these three were together, just like this. Finally, Glossopteris was found in all the southern continents, and that shows that they were once joined. Now, Glossopteris was a tropical plant, so this plant wouldn't survive in even a climate like we have here in Minnesota. It would have to be in a much warmer area, and that suggests that all three of these were together in a nice warm area. So Antarctica wasn't always as cold as it is today.